Let us look at normal subgroups. Now, before we actually look at normal subgroups, let's understand something else first. In algebra, we have seen that given a fraction 1 by a plus b root c, we simplify the denominator by multiplying the fraction by the conjugate of the denominator, which doesn't change the value of the fraction itself. What do I mean by that? We do something like this. 1 divided by a plus b root c times a minus b root c divided by a minus b root c. So here, the value of this is not changing because this is as good as multiplying it by 1. This could have been written as in this form, and it would mean the same thing. So here, a minus b root c on the left hand side times 1 by a plus b root c times a minus b root c inverse, which is nothing but the reciprocal of this. So if we write it like this is the group theoretic style. But we generally write it as a minus b root c divided by a minus b root c because multiplication is commutative. Whether we use this or whether we use this form, this and this gets cancelled because of the commutativity of multiplication. Okay, so that means the value of this doesn't change. But in group theory, remember, we don't assume commutativity. The group operation may be commutative, may not be commutative. So in group theory, conjugation has a similar flavor, similar to this. So we have a group under an operation star is a group and H is a subgroup of G. So for a fixed X in G, the conjugate of H by X or conjugation of H by X is written as X times the subgroup H times X inverse is equal to X times an element of the subgroup H times X inverse, where H is in H subgroup and X is in G. Keeping this in mind, now we can say if for every element of G, we have X times the subgroup X, H times inverse of X is equal to H, then H is a normal subgroup of G. And this is written as H normal subgroup notation G. Or we could also say if H is a normal subgroup of G, then for every X in G, conjugation is or gives us an element in H itself. So if the subgroup is normal, then left and right cosets are equal. So in this case, we use N. Normally, if we know that something is a subgroup of a group, you might have noticed in all the previous sessions, we have been using H for a subgroup and G for a group. But if we know that that subgroup is a normal subgroup, then we use capital N as the name for the subgroup rather than H. So here, this would be written as N is a normal subgroup of G if for all X in G, X times N times X inverse is equal to M. Now, remember I said, if the subgroup is normal, then left and right cosets are equal. How can I say that? This is how. Now, as per the definition, we have X times the normal subgroup times X inverse equal to N. Now here both left and right sides, we multiply it by X or carry out the group operation with X on both sides. So what happens? This X inverse times X becomes E and anything operated with E remains unchanged. So we are left with x times n is equal to n times x. And what is this? This is the left coset and this is the right coset, and they are both equal. So that is how we can say that if the subgroup is normal, then left and right cosets are equal. Now, if the subgroup does not change under conjugation, implies left and right cosets are equal. So based on this, I have written this statement. Now let's look at an example. The group S3, let n is equal to the subgroup generated by 1, 2, 3 permutation. That is equal to E, 1, 2, 3 and 1, 3, 2. So this is n is a subgroup of S3. So now we have to check for every x in S3, we have to check whether x times n times x inverse is equal to m. So let's do that checking. The identity fixes everything. So conjugation by E is given. That's why it's called trivial. Now let's take x equal to 12. Conjugating 1, 2, 3 with x, we get 12 times, or rather permutation 1, 2 times, permutation 1, 2, 3 times, permutation 1, 2 inverse. Now if we evaluate this, we get the inverse of 1, 2 is 1, 2 itself. And if we evaluate this, we get 1, 3, 2 permutation. And 1, 3, 2 is in n. Let's take the next one. X equal to 1, 2. Conjugating now 1, 3, 2. We get 1, 2 times 1, 3, 2 times the inverse of 1, 2. Inverse of 1, 2 is 1, 2 itself. So if we evaluate this, we get 1, 2, 3, which is again in n. Now let's take another element from G. X is equal to 1, 2. X is equal to 1, 3. Conjugating 1, 2, 3, we get 1, 3 times 1, 2, 3 times the inverse of 1, 3. Which if we evaluate, we get 1, 3, 2 permutation, which is there in n. Again, let's take x equal to 1, 3. Conjugating 1, 3, 2 now. We get 1, 3 times 1, 3, 2 times the inverse of 1, 3, which gives us 1, 2, 3, which is again in n. Okay. Now, if we take x is equal to 1, 2, 3. Now remember 1, 2, 3 is there in the subgroup n. So conjugating it will in any case will satisfy the condition that it is an element in n. Why? Because n is a subgroup of S3. And same is the case with respect to 1, 3, 2. So we have checked in all the cases this condition is being satisfied. So which means for every x in S3, we have x times n times x inverse equal to m. Therefore, we can say that n is a normal subgroup of S3. H is not a normal subgroup of G. Then conjugation gives us a different subgroup of G, which means there exists at least one x in G such that x times h times x inverse is not equal to h. So let's see this example. Again in S3, let h is equal to the subgroup generated by the permutation 1, 2, which gives us E, 1, 2. So taking x is equal to 1, 2, 3, we get 1, 2, 3 times E times 1, 2, 3 inverse. This E is from again H, which gives us 1, 2, 3 times E times 1, 3, 2, because the inverse of 1, 2, 3 is 1, 3, 2. And this is equal to E. 1, 2, 3 times 1, 2. So first we took E, now we are taking 1, 2. So 1, 2, 3 times 1, 2 times 1, 2, 3 inverse, which gives us permutation 2, 3. But remember, 2, 3 is not there in this subgroup H. E was there, but 2, 3 is not there. So 1, 2, 3 times H times 1, 2, 3 inverse is equal to E comma permutation 2, 3, which is not equal to H, but is another subgroup of S3 of order 2. So remember, when this condition is satisfied, then it is a normal subgroup. When it is not satisfied, it is still a subgroup, but it is not a normal subgroup. Now let's look at some interesting aspects. Intuitively speaking, just like multiplying by a conjugate doesn't change the fractions value, in a normal subgroup, conjugating by any group element doesn't change the subgroup. Let's look at some equivalences. If for every x in G, we have right coset equal to left coset, then N is a normal subgroup of G, even when G is non-abelian. N is a normal subgroup of G if and only if each right coset of N in G is a left coset of N in G. Same thing written in a different way. N is a normal subgroup of G if and only if the product of two right cosets of N in G is again a right coset of N in G. That is, N times A times N times B is equal to N times A times B. If this condition is satisfied, then also we can say N is a normal subgroup of G. Now let's look at some general properties. If two right cosets have one element in common, then they must be identical. That means if one element is common, then the others also have to be common. Every subgroup of an abelian group is a normal subgroup. Since in an abelian group, the operation is commutative. Let's say we have N1 and N2. Both are normal subgroup of G. That implies that the intersection between N1 and N2 is also a normal subgroup of G. And if N and M are normal subgroups of G such that intersection of N and M is equal to E, then every element of N commutes with every element of M. That is, N times M is equal to M times N for all N in N and M in the subgroup M. Make sure that you understand all this. And what I would highly recommend is that when you look at these properties, take an example and actually figure out two subgroups, two normal subgroups, and take the intersection and see whether the statement is true or not. So that was normal subgroups. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.